And we're starting with Chapter 1, Section 1.1, which is just looking at one linear equation. And by a linear equation, well, you've seen simple examples in high school math, like 2x equals -9 is a linear equation in one variable, x. Or 4x plus 7y equals 5 is a linear equation in two variables, x and y. And 3x minus 2y minus 5z equals 0 has three variables. And in general, one can have any number of variables in a linear equation. So the general linear equation the general form of a linear equation is a1x1 plus a2x2 plus a3x3. If it has n variables up to an xn equals b. So this is what a linear equation looks like. And the first thing we do is study the solutions of one linear equation. It doesn't matter what letters we use for the variables. It could be x, y, z. It could be x1, x2, x3, and so on, or y1, y2, y3, or t1. Doesn't matter. And we often, for conciseness, sometimes use what in calculus was called sigma notation. You would write this as, this is the Greek letter sigma. Let's say j goes from 1 up to n. A sub j, x sub j equals b. So this equation and this equation are exactly the same. We just used a different notation to write them down in. Okay. Now, let me emphasize that as I'm doing these lectures in these Zoom classes, anytime you have a question, just interrupt, unmute yourself, interrupt, and ask. You could also write a question in the chat, but it's easy not to notice the chat. At least it's easy for me not to notice the chat. But if you have a question about anything we're doing, just interrupt and ask. Sometimes equations are divided into two types. So if your equation is a1x1 plus a2x2 up to an xn equals 0, this equation is called homogeneous. It means this is 0 on the right-hand side. And if it's a1x1 plus a2x2 up to an xn equals some number b, which is not 0, then this equation is called inhomogeneous. So in every subject, there is terminology you have to learn, and that's what it is. And what do we mean by a solution of an equation? A solution, let's call this equation 1.1. A solution of this equation 1.1 is a sequence of numbers x1 up to xn that solve the equation. And we usually write the solution in the form is a vertical sequence of numbers, x1, x2, x3, down to xn. And this is called a vector, or sometimes an n-dimensional, because they're n numbers, column vector. That's what we mean by a solution of the equation. So for example, if you have the equation 4x plus 7y equals 5, the vector 3 minus 1 is a solution, because if you plug in the numbers, 4 times 3 plus 7 times minus 1, that's 12 minus 7, that's 5. So it really is a solution. So we write our solutions typically as column vectors. And to a very great extent, linear algebra, it starts with linear equations, but it's really the study of vectors. And what we are very interested in is what is called the solution space of an equation is the set of all vectors that satisfy the equation. And let me emphasize the fact that everything I'm doing in these lectures is coming from the lecture notes that I posted. So it's not, you can take notes as much as you want. It depends on how you like to learn material. But these videos of the lectures will be posted on YouTube, and the complete text, legible. My handwriting isn't so legible, but the complete text printed out is in the lecture notes on the website for the course. Okay. There's one kind of equation which is sort of silly in a certain sense, but we often need to consider it or exclude it. So what is sometimes called a zero equation is the equation a1 x1 up to an xn equals b, with not with the b's, but with a1, a2, all of the coefficients of the variables equal to 0. That's what is called the zero equation. So if b is not 0, then the zero equation has no solution. That is, suppose you want to solve the equation 0 times x plus 0 times y equals 1. Well, no matter what you choose for x and y, the left-hand side is 0, and you'll never get 1. So this has no solution. And in general, if you have a zero equation, if this number b is different from 0, there's no solution. If b equals 0, every vector x1 up to xn is a solution, because 0 times x1 plus 0 times x2 up to 0 times xn, no matter what the numbers x1 up to xn are, this is always 0. So if you have a zero equation, if it's homogeneous, every vector is a solution. And if it is inhomogeneous, no vector is a solution. So we'll often say, let's just consider non-zero equations, because there's not much to say about a zero equation. Okay, so this is a technical point, but it's important to get it out of the way. Any questions about this? So the first lemma is a result that's important, but maybe not as important as a theorem, is that every non-zero equation has a solution. So if you want to know if linear equations have solutions, the answer is yes. Except for the zero equation, they always do. And there are really two cases. In the first case, there's just one variable. So if there's only one variable, the equation looks like a1x1 equals b, and it's non-zero, means a1 is different from 0. And you learn in high school how to solve this equation. The solution is x1 equals b over a1. And that's the only solution. It is the unique solution. So an equation in one variable always has exactly one solution. Not two solutions, not three solutions, not infinitely many solutions. And in the second case, you have two or more variables. So your equation looks like a1x1 plus a2x2 an(xn) equals b. And one of these coefficients at least, it's called a sub j naught, is different from 0 for some number j naught between 1 and n. So there's some term, there could be more than one, could be all of them, but there's at least one term in this equation where the coefficient is different from 0. And now you can do the following thing. You can solve this equation for j naught. So you have a sub j naught x of j naught is equal to b minus the sum of all the other terms. All the terms from j going from 1 up to n, a sub j, b sub j, except j naught. And a sub j naught is different from 0, so you can divide by it. One over a sub j naught. And this is a solution. So, oops, x sub j. So for every choice of the numbers x1 up to x sub n, except for j naught, there exists a unique solution of the equation. Which tells us that if n is greater than or equal to 2, if you have at least two variables, then the linear equation has infinitely many solutions. Okay. So let me point out two things about this. One is I stated a lemma and I gave a proof. So linear algebra is a 300 level math class. In math, it's not just a matter of learning techniques. You also have to learn how to prove theorems. And all of the exams, for example, as well as the homeworks, will generally include solving problems and proving things. So you have to learn in the course of the semester, which is just 4 weeks long, methods of proof. And when you do this for the first time, it can be very difficult. So if this is the first math class you've taken in which proofs are required, then you really need to invest a lot of time to understand the proofs in the book, line by line, statement by statement, and understand them well enough that you can not only reproduce the proof, but actually use the techniques in the proof to prove new results, right? That's what we do in mathematics.
Professor?
All right. Are there any questions?
Yes. Can you hear
Yeah,
me?
go ahead. But speak up a little bit more loudly, please.
Okay. I was gonna ask, do you think that you can try and re-explain case two by any chance?
To explain case 2 here, this one?
Yes, when you were doing like the work, I was kind of like getting confused.
Okay, no, happy to. I'm very glad you asked.
Thank you.
So suppose we have a linear equation in n variables where n is at least 2. So let me just give an example. Suppose we take n equal to 3, and maybe our equation is 7x plus 2y plus 3z equals 16. Right? And we want to solve this equation. So you pick a variable where the coefficient is different from 0. So in this case, x, y, and z all have coefficients different from 0. Here the coefficient is 7, here the coefficient is 2, here the coefficient is 3. So I'll let you pick a variable, x, y, or z. Which one do you like?
Z.
Z, okay. So let's try to solve this equation for z. This says 3z is 16 minus 7x minus 2y, right? I just brought these two terms to the other side. And because the coefficient of z is 3 and it's non-zero, I can divide by 3. So z is 1/3 16 minus 7x minus 2y. And what this says is for every choice of x and y, there exists a number z such that the vector x, y, z is a solution. So I'll let you pick. Give me any two numbers you like for x and y. What should x be?
5.
Pick a number, your favorite number.
7. 7.
Okay, and pick a number for y.
5.
Okay, so in that case, we let z be equal to 1/3 16 minus 7 times x, that's 7 times 7, minus 2 times y, that's 2 times 5. So this is 1/3 times 16 minus 49 minus 10. So 16 minus 49 minus 10 is, I think it is let's see, 6 minus 49 is minus 43.
Yeah.
Is that right?
Yes.
So Z, so we have X equals 7, Y equals 5, Z equals minus 43 thirds. So I claim this is a solution. So let's plug it into the equation and check. 7x is 7 times 7, plus 2y is 2 times 5, plus 3 times minus 43 over 3. This is 49 plus 10 minus 43. 49 minus 43 is 6 plus 10 is 16. That's the equation. That's what it's supposed to be. So this is a solution.
Okay, so
right?
that makes
So I'm sorry, go ahead.
sorry, that makes sense. The only question I have is where does the n equals 3 come into play? Is that because
N is just the number of variables. So here there are 3 vectors,
oh
1, 2, and 3,
okay.
right? And in the general case, you have n variables.
Okay.
X1, X2, all the way up to X sub n. There n is the number of variables.
Okay.
And what we proved is that if you have a linear equation, a non-zero linear equation with 2 or more variables, then there are in fact infinitely many solutions. Because what we saw in this example, I let you pick X and Y. I didn't tell you what to pick. And for every X and Y, I could compute a Z. And there are infinitely many ways you could choose X and Y. So there are infinitely many Z's, and that means there are infinitely many solutions.
Okay, thank you.
Okay. Now, we write solutions as these column vectors, and we let Rn, this is the set of all n-dimensional column vectors. That means all vectors, x1, x2, these are column vectors, just n numbers written in a line for all choices of x1, x2, up to x sub n. So I use the standard notation in mathematics where a set is a collection of objects, and you define a set by putting things inside these curly brackets. And this is the set of all of these n-dimensional column vectors, x1 up to xn, are any real numbers. In linear algebra, we also consider the complex numbers. And I'll include, if you're not familiar with complex numbers, before we start to use them, I will have a lesson in which I explain what they are. And you can also consider Cn, which is all n-dimensional vectors, where these numbers, which are called the coordinates, are complex numbers. And in linear algebra, from the very beginning, you have to consider real numbers and complex numbers both. At this point, there's no difference really. So I'm going to state everything in terms of real numbers, but it also applies to complex numbers. And you have to learn the algebra of vectors. So let's just start with like 2-dimensional vectors. Like here's a vector 2, 3. And here's a vector 7 minus 5. And the way you add 2 vectors is you add their coordinates. So here, the first coordinate is 2. Here, the first coordinate is 7. when you add them, the first coordinate is 2 plus 7. Here, the second coordinate is 3, and here the second coordinate is minus 5. So when you add them, you get 3 plus minus 5. 2 plus 7 is 9. 3 minus 5 is minus 2. So the sum of these two vectors is this. Okay? Right. Any questions about this? Let's just do a few examples. Suppose you take the vector 19 minus 3 and minus 7 minus 8. And when you add them, what do you get? You get 19 minus 7 minus 3 minus 8. That's 12 minus 11. Suppose you have the vector 1, 2 and the vector 3, 4. When you add them, can someone tell me what you get?
You get 1 plus 3 and then 2 plus 4, which would give you 4 and 6.
Exactly correct. That's 4, 6. And the same rule applies for vectors of any dimension. So if you have the vector 1, 2, 3, and you're going to add 4, 5, 6, you add the first coordinates, 1 plus 4 is 5. Second coordinates, 2 plus 5 is 7. Third coordinates, 3 plus 6 is 9. So these are three-dimensional vectors. And it doesn't matter how many coordinates you have. If you have a 5-dimensional vector, 1, 0, minus 8, 9, 11, and you have another 5-dimensional vector, 2, 3, minus 4, minus 4, minus 7, you have to add vectors of the same dimension. You cannot add a 3-dimensional vector plus a 5-dimensional vector. But here we have two 5-dimensional vectors. What is the sum? First coordinates, 1 plus 2 is 3. Second coordinate, 0 plus 3 is 3. Third coordinate, minus 8 minus 4 is minus 12. Fourth coordinate, 9 minus 4 is 5. Fifth coordinate, 11 minus 7 is 4. So these are vectors in R5, 5-dimensional vectors. And when you add them up, this is what you get, right? So that's the rule for addition of vectors. Now, in linear algebra, we often use a word for number, which is scalar. So scalar is just another name for a number. And what I've described here is vector addition. This is the rule for adding vectors. And there also is an operation called scalar multiplication. When you take a vector and multiply it by a scalar, which means a number. So for example, suppose you have the vector 2, 3, minus 5, and we want to multiply it by 6. All that means is you multiply each coordinate by 6. 6 times 2 is 12. 6 times 3 is 18. 6 times minus 5 is minus 30. Right? This is scalar multiplication. If you have the vector 0, 2, minus 8, 5, minus 1, and you multiply it by the scalar minus 3, you just multiply every coordinate by minus 3. 0, minus 6, 24, minus 15, 3. Right? So if we want to write down the general rule for addition and scalar multiplication, of column vectors, it's the following. We usually denote a vector x by some boldface x. I can't do it very well with a piece of paper, but if x is the vector x1 to xn, sometimes you put arrows over them if I'm writing on a blackboard just to emphasize it's a vector. And y is y1 down to y sub n. Then the sum of the vectors x plus y, that's x1 to xn plus y1 down to yn. You just add coordinate wise, x1 plus y1. In general, for the ith coordinate, it's xi plus yi, all the way down to xn plus yn. And for any scalar or number c times the vector x, that's c times this column vector. You just multiply every coordinate by c. So this is vector addition, and this is scalar multiplication in Rn. This is like this, the space or set of n-dimensional column vectors. Okay. You can also subtract vectors, and you do it in the obvious way. If you have x1 down to xn and y1 down to yn, you subtract just by subtracting the coordinates. So for example, if you had the vector 2, 7, and you wanted to subtract the vector 3, 4, first coordinate is 2 minus 3. The second coordinate is 7 minus 4. So this is the vector minus 1, 3 in R2. So you're used to adding, subtracting, and multiplying numbers, and with the correct understanding of how these things work, you can do the same thing with vectors. Again, for us, the basic problem right now is to find all solutions to a linear equation. That is, and the set of all solutions is called the solution space. Find the solution space of the linear equation (4x plus 7y equals 5). Now, there are always, in mathematics, many different ways to solve a problem. And in general, how you solve a problem is up to you. I only care about your getting the solution, right? I mean, you get the solution, that's the right answer. You don't have a solution, that's the wrong answer. Any way that works, works. So let's do what we did in high school. Solve this equation for y in terms of x. You would get 7y is 5 minus 4x, or if you divide by 7, y is equal to 5 over 7 minus 4 over 7x. So what is the solution of this equation? The general solution, because for no matter what I choose for x, this gives me a y. So x y, this solution is x, and y is 5 over 7 minus 4 over 7x. I'd like to simplify that a little bit. Let me do it like this. This is, see here I have 5/7 minus 4/7 x. Here, let me write this as 0 plus x, because 0 plus x is the same as x. And if I do it like this, I can write this as two vectors. It's the vector 0, 5/7 plus the vector x minus 4 over 7x. And I could factor an x out of this if I like. This is 0, 5/7 plus the scalar, the number x, times the vector 1 minus 4 over 7. Oh. So this is kind of interesting. I mean, this is just a simple equation. You saw that in high school, but we're using vectors to describe the solutions. So let me just repeat this on where I have a little bit more space. I had the equation 4x plus 7y equals 5. When I solve for y in terms of x, I got y is equal to 5 over 7 minus 4 over 7x. So my general solution to this equation is the vector xy equal to x, and y then is equal to 5 over 7 minus 4 over 7 times x, which I could write as the vector 0, 5/7 plus the vector x minus 4 over 7x. I can write this second vector. So I have 0, 5/7 plus the vector 1 minus 4 over 7 times x. So every solution of this equation is a vector of this form. And every vector of this form is a solution of this equation. I could, if I don't like fractions, I could simplify this slightly. I could write this as follows, because 1 is the same as 7 over 7. And if I factored out a 1 over 7, this would be 0, 5 over 7, plus x over 7, that number, times the vector 7 minus 4. And then I observe that as x runs through all possible real numbers, so does x over 7. So the solution space can be written as the set of vectors 0, 5 over 7, plus x times the vector 7 minus 4 for every real number x. And this is the solution space. So this is the first thing we have to learn about solving linear equations. We want to find the solution space expressed as a set of column vectors, and this is an example. Right? And again, this example is worked out in legible, complete detail in the notes, so you can see what's going on. Any questions about this? I'm going to do several more examples. So this is one solution to the problem of finding the solution space of this linear equation. Let's look at another example. Again, this is an example from the book, so it's easy to follow when you're studying by yourself. Let's take an equation in 3 variables, 3x minus 2y minus 5z equals 17. And we want to find the solution space. The solution space will be a set of 3-dimensional column vectors. That's it. It's in R3. This is 3-dimensional column vectors. So one thing we could do is solve for z. If you solve for z, what do we get? We get 5z is 3x minus 2y plus 17. Minus 17. Bring this on the other side, bring this over here. 5z is minus 17 plus 3x minus 2y. So z is minus 17 over 5. I'm just dividing through by 5 plus 3 over 5x minus 2 over 5y. So the solution x, y, z, I can choose any number for x and I can choose any number for y, but then z is required to be this. And I'd like to get this solution space as some, what's called a linear combination of vectors. Let me write it like this. This is, see here I have minus 17 over 5 plus 3 over 5x minus 2 over 5y. Here I have x. Here I have y. So this is like 0 plus x plus 0 and 0 plus 0 plus y. So x, y, z is this vector, but I can see this is really representable as a sum of 3 vectors, right? Just by looking at it like this. So visual observation is important. This is 0, 0, minus 17 over 5, plus this x, 0, 3/5 x, plus this 0, y, minus 2/5 y. And I can factor out an x from this vector and a y from this vector. This is the vector 0, 0, minus 17 over 5, plus x times the vector 1, 0, 3/5, plus y times the vector 0, 1, minus 2/5. So the solutions of this linear equation in 3 variables, it's all vectors which consist of this vector, a scalar multiple of this, and a scalar multiple of this. And again, if I don't like fractions, I don't dislike them, but if I wanted to get rid of the fractions, minus 17 over 5, I could factor out a 1/5. This would be x over 5 times 5, 0, 3. And I could factor out a 5 from this, plus y over 5 times the vector 0, 5 minus 2. And x and y could be anything, so one way to express the solution space is like this. The set of all solutions of this linear equation in 3 variables is all vectors of the form, this vector plus any scalar multiple of this plus any other scalar multiple of this. That is the solution space. And in the homework for tomorrow, you have to solve many linear equations, which means find the solution space and write it as this sum of vectors.
I have a question.
Sure.
Okay, so.
But can you speak up a little bit? I find it hard to hear what you're saying.
Yes. Okay. You kind of lost in me a little bit because I never learned vectors before, so
Yep.
it's still like new to me. So do you think you can kind of go over it again?
So if you took, I mean, I don't think it's a prerequisite, but if you took Calc 3, that's calculus of vectors.
Yeah,
but,
I never did.
But in any case, all a vector is, so a vector in Rn is just a column of numbers. X1, X2, up to Xn. It's just taking n numbers and writing them as a column. And the order is important, like 3, 5, 2 is not the same as 5, 3, 2, right? Two vectors the same only if their coordinates, like the first coordinates are the same, the second and the third. So it's just a column of vectors. That's all it is. So psychologically, it might be complicated in the beginning because you're not used to it. But I mean, just the way 2 plus 5 is 7 and 3 plus 1 is 4. If you take the vector 2, 3 and the vector 5, 1, and you add it, you get 7 and 4. Because 2 plus 5 is 7 and 3 plus 1 is 4. That's all it is.
Okay, thank you.
Right? So there's a more abstract form of vectors that we'll get to later in the semester. If I say we'll get to it in a month, that means in 3 or 4 days in summer school. But the prime example of a vector is a column vector in Rn. And Rn, the set of all common vectors, column vectors, is the primary example of an n-dimensional vector space. Let me do one more example, and then we'll stop for the morning session. This is the first homework problem, I think. Solve the equation x plus y equals 0. So in this equation, and we want to write the solutions in vector form. So in this equation, for any x, y has to be minus x. So if you look at the vector xy, x is x and y has to be minus x, which is the same as x times the vector 1 times minus 1. So the solution space is the set of all vectors x times 1 minus 1 for all real numbers x. So the solution space of this very simple equation is exactly the set of all scalar multiples of 1 minus 1. So this is exercise 1.1a in the homework. Okay. All right. Well,